October 1215. Rochester Castle, Kent. King John's army has broken through the outer defences. Rebel barons retreat into the great stone keep. Outside, siege engines begin working. Inside that tower is something almost as important as the walls themselves. A well the siege will last for weeks. The attackers can smash stone, they can burn timber, they can block the roads and wait. But if the defenders still have water, the castle can keep functioning. This is how medieval castles stayed supplied with fresh water during a siege. A castle looks like a military problem. Thick walls, arrow loops, towers, gates. But once the doors close, it becomes a logistics problem. People need water every day. So do horses. Kitchens need it, bakers need it, wounds have to be cleaned, fires have to be controlled. And the more people packed behind the walls, the faster the supply disappears. An attacking army understands this. Food can be stockpiled. Grain keeps. Salted meat keeps. Water is different. It is heavy, consumed constantly, and difficult to replace once the enemy controls the ground outside. So the safest solution was straightforward. Put the water source inside the defenses. At Rochester, the enormous Norman keep contains a well shaft built into its central spine wall. This meant defenders did not necessarily have to leave the strongest part of the fortress to reach water. The source itself was protected by several meters of masonry. The idea sounds simple. Building it was not. A well works by reaching groundwater. On low ground, that might mean digging through soil and softer material. But castles were often placed on high ground, rocky ridges, or elevated positions because those sites were easier to defend, excellent for warfare. Bad for digging wells. The higher the castle stood above the local water table, the farther workers might have to descend. At Goodrich Castle in Western England, the surviving castle well reaches roughly 166 feet, or about 51 meters, below the courtyard. Water was raised with a bucket, chain, and windlass. That means every container used in the castle began with the same slow process. Lower the bucket, fill it, haul it back, then carry the water where it was needed. There was no tap, and Goodrich was not unusual in treating the well as critical infrastructure. At Denbigh Castle in Wales, the surviving well is described as the castle's only water supply. One shaft could determine how long an entire fortress remained usable, but not every castle could simply keep digging until water appeared. Geology could make that difficult, expensive, or effectively impossible. Some fortifications stood on rock where a reliable underground source was awkward to reach. Others had access to natural springs. So medieval builders used another system. They collected water. At Criccieth Castle in Wales, a cistern inside the entrance area was supplied by a natural spring. Instead of depending on a deep shaft alone, water could collect in a protected chamber where it remained accessible from inside the defenses. Rain could also become part of the system. Roofs already moved large quantities of water during bad weather. Stone channels, gutters, and drains could direct some of that water towards storage areas or cisterns instead of simply throwing it outside. This turned part of the castle itself into a catchment surface. The roof collected, gravity moved, the cistern stored. The principle was basic. Its value during a siege was not. Imagine a fortress surrounded for several weeks. Every external stream is now dangerous. Every path to a spring can be watched. A person leaving the gate with buckets is no longer just collecting water. They are entering enemy-controlled ground. An internal source removes that problem. But there were more sophisticated options. Medieval communities also knew how to move spring water through pipes. At St. Augustine's Abbey in Canterbury, a mid-12th century system collected clean spring water in a masonry tank and carried it toward the abbey through a pipe. Medieval pipes could be made from lead or hollowed-out tree trunks. A fortified site with access to a higher spring could use the same basic principle. Gravity does the work. But that creates a weakness. The source may be protected, the conduit may not be. If attackers discover an exposed section outside the walls, they may be able to interrupt the supply. Any water system extending beyond the defensive perimeter is only as secure as its most vulnerable section. This is why an internal well had such military value. A protected shaft was harder to contaminate from outside. There was no external pipe to cut. And groundwater was far harder to blockade than a road, stream, or exposed spring. Still, having a well did not mean having unlimited water. Someone had to raise it. A deep well turns water into labor. One bucket might serve a kitchen. Hundreds of buckets have to serve a garrison. Now add horses. A castle prepared for war might contain not only soldiers, but servants, craftsmen, animals, and civilians seeking protection. The population behind the walls rises just as access to the outside world disappears. The system that works comfortably in peacetime is suddenly under maximum demand. Then something else happens. The enemy begins throwing fire. Timber roofs, wooden buildings, stored materials, and internal structures can burn. Water is no longer only something people drink. It becomes part of the castle's firefighting system. Every bucket thrown onto flames is a bucket someone had to pull from below. This is the hidden side of siege warfare. Attackers are not always trying to climb the wall. Sometimes they are attacking arithmetic. How much grain remains? How many animals can be fed? How many people are inside? How quickly is water being consumed? At Rochester in 1215, King John's forces battered the castle and undermined the southeast corner of the keep. Timber supports beneath the masonry were burned, and part of the corner eventually collapsed. The defenders withdrew deeper into the building. The stone failed before they did, but the siege continued. And eventually, the decisive weapon was not another machine. It was shortage. The defenders were starved into surrender after holding out for roughly 2 months. That tells us something important about castle water systems. Water could remove one of the attacker's most effective clocks, but it could not remove every clock. A castle needed a chain of supplies: water, food, fuel, storage. People capable of moving all of it break one critical link, and walls several meters thick become less important with every passing day. The same principle could shape an entire fortress. A protected, well-secured one supply line. Access to a river, harbor, or higher spring could secure another. The engineering problem was never just how to keep the enemy out. It was how to keep everything inside working. And that changes the way a castle looks. Battlements, towers, and gatehouses are obvious because they rise above the ground. They are built to be seen. The systems keeping everyone alive often disappear in the opposite direction. Down. Today, the floors inside Rochester's keep are gone. The roof is gone. One corner still carries the scars of the siege and the rebuilding that followed, but inside the massive central wall, the well shaft remains. 8 centuries later, it still disappears into darkness. The walls tell us how the castle resisted an army. The well tells us how the people inside my resisted time. And even now, from the top, you cannot see where the water begins.